So in this application problem, we're going to take a look at how real-life problems apply to absolute value equations and inequalities. So read each real-world situation and carefully examine each defined variable and function. Example: an absolute value function can be used to show how much a value deviates from the norm. The average internal body temperature of humans is 98.6 degrees Fahrenheit. As a function, the equation is V of t equals the absolute value of t minus 98.6, where V of t is the variation in temperature from the norm and t is the temperature of the patient. Part A. The temperature can vary by as much as 0.5 degrees and still be considered normal human temperature variation. Write an absolute value equation to model normal human temperature variation and solve this equation and graph the solution set below. So this is a great example of an SAT or standardized test question in which they actually give you the equation and they just ask you to solve. So sometimes there's work to do, but in this case, all you have to do is take this number and put it in for variation. So it's just going to end up looking like this, and then you just have to know how to solve it using an absolute value model. So that's not so bad, other than the fact that it's a word problem and you have decimals. Okay, so how do we solve absolute value? Remember, absolute value is defined as the distance from zero. So what it's saying is that 0.5 is equivalent distance from 0 as negative 0.5. So I have to solve both of those equations because the absolute value is basically saying that those are the same equivalent distance from 0. So in this case, they would be the same value. All right, so we take 0.5 and we set it equal to t minus 98.6, removing the absolute value symbol, because now we're going to set up a second equation in which negative 0.5 would also equal t minus 98.6. And then we just solve this equation, and it's actually just, both these equations are just one-step equations. I'm going to add 98.6 to both sides. So I add it here and it cancels, and I add 98.6 here. And that will give me the upper variation of human acceptable temperature, and that would be, add these two together and you get 99.1. So 99.1 is still considered a normal temperature. And if you've ever exercised or woken up from a bad dream where you've gotten really hot potentially, you might have a temperature of 98.1, and it's not considered ill, it's just considered a variation within your temperature. And some people will actually run a higher temperature normally as well. So same thing on the lower end here, but in this case I would get 98.1, and that is equal to the lower end of temperature. So if I were to graph this on a graph, on a number line, it probably would make sense to maybe use a unit of just one, or maybe we'll just go by 0.5s. So this would be 99 degrees. This would be 99.5. And then 100. And then here we would have 98.5. And then below that we'd have 98 degrees. And so if I were to graph this pretty easily, I'd put 98.1 right here as a dot, and 99.1 right here as a dot, and it would just look like that. That would be the two upper and lower ranges. To color it in and go beyond it, that's the actually second part of the equation. So these would be the range of temperatures, but to make it look more, to make it a little bit, by the way, if you want to put a unit, you just put a degrees Fahrenheit on there. That's the second part of the problem. So if I look at the next part of the problem, hypothermia, dangerously low, or hyperthermia, indicating a fever, occurs when the body temperature is outside of the range mentioned in Part A. Write an absolute value inequality to model temperatures in this range, and solve this inequality and graph the solution set below, and use set notation to denote the answer. So what they're talking about, let's do the visual first. If I take a look at this visual that I have over here, 98, 98.5, 99.5, right, so 98, 98.5, and then 99. If I take 99.1, and I'm going to use an open circle because remember 99.1 is considered acceptable. If I go this way, I have hyperthermia, hyper meaning above. And if I have 98.1 here, again, open circle because at 98.1 I'm still considered okay, and I go this way, that would be hypothermia. So if I think about this in terms of an inequality answer, that would be if my temperature is below 98.1 degrees, or if my temperature is greater than, right, greater than 99.1 degrees, I would have these two medical situations. Both are dangerous. So that's the answer. The question is, well, what is the inequality? All I would have to do is take 0.5 and make it, right, and I have to put an inequality here. And so the question is, what inequality do we use to denote this outside of range? And it's a little confusing because typically to do inequalities, what we're going to do is we would want that number to be over here, and it would make a little more sense. So I'm actually going to place it over here, and I'll show you why that's important. So the question is, well, what would it be? So if we were to look at the two solving methods, right? Remember, we're going to do the same thing. We're still going to have the exact same situation that we had over here. T minus 9, sorry, it should be 98.6. Let me fix that. All right, so what's going to happen is we're going to have T minus 98.6. And remember, we want to make sure that when we add this and get 99.1, that it is greater than this. So I guess the question is if we start off that way, will that in fact give us the right inequality? So let's just start off by saying greater than, because we know that from the graph, 0.5. Okay, so if we add that to the other side, we would have greater than 99.1. So yeah, that looks like it works. So the question is, knowing how absolute values work, if we make this a greater than symbol, what's going to happen in the world of absolute value is that would have to reverse, right? That would have to reverse around and become negative. That's what we learned about absolute value earlier in the unit. So if I add that to the other side, I would have t is less than, add 98.6 and negative 0.5, I'd have 98.1. It's kind of interesting. I kind of worked this problem backwards from the graph, but this is the equation right here. This is the equation that would produce the graph that we could already sort of visually see from this side. Notice I did not use an equal sign because of the fact that I don't have these values, if they're inclusive, are over here, meaning that you're healthy. All right, there's one last part to this. It says, at home you discover your old thermometer is is measuring temperature incorrectly by 2 degrees, and this will alter the model to be V of t is equal to t minus 98.6 minus 2. If a person is told that their variation in temperature is 1.1 degrees, use the equation to find their actual body temperature. Okay, so what that's saying is it just wants me to put this value in for the variation. So 1.1 is equal to the absolute value of t minus 98.6 minus 2, and then I'm going to solve this equation. Now this is an important thing to understand because these absolute value bars, you can't just add the 2 to both sides and get going. You can't just make this plus or minus. There's a certain way that has to be done. You have to solve for the absolute value symbol. So you have to actually add the 2 to the other side before you begin the solving process for the absolute value. So this now becomes 1.3 is equal to the absolute value of t minus 98.6 And now I can actually solve it. That feels very awkward in a real life problem, but when you study how to solve absolute value, you have to solve for the absolute value symbols before you apply the fact that you have a positive and a negative one. It's a really critical step that's forgotten by a lot of students. So make sure that you solve for those absolute value symbols first. Okay, so there's my first equation, and my next one is negative 1.3 is equal to t minus 98.6. And then I just solve both of these. So if I add 98.6 over here to both sides, pretty easy to do because everything lines up. So you get a 0.9 here, and then here you get a 9, and then here you get 99.9 as your upper range for your temperature. Then if I add 98.6 over here, now this one's a little bit confusing because of the fact that it's a negative one, so we're definitely going to break out the calculator. So negative 1.3, again, you could use Desmos or use a Casio or whatever you prefer. So this lower range of temperature is 97.3. So that would be the lower range, and this would be the upper range. So to answer the question, use equations to find out the actual body temperature. The body temperature, where you can't figure out the actual body temperature, you can only figure out that it is between these two things. So if you were to use interval notation on that, you would use, you would say it's between 97.3 and 99.9, and we could probably go ahead, since we have an equal sign, and use a bracket for that. And that reminds me, up here, I use this notation, and the answer asked me to put it in set notation. So this one would be anything below 98.1. That's a weird thing to put in set notation because human body temperature, obviously, you would at some point not be alive. So I think I'm just going to keep it in this notation.